challenge is called Breaking Well. We're going to take it up a notch. I think just a few challenges ago, they had one where we just added 3 numbers. And so we're going to get a little bit more into math for this one, but that's a good thing. I'll read you the instructions. In my opinion, they're not worded very well, so I'm hoping the work makes that clear. I think that a lot of the people who make the challenges maybe have English as a second language, so they make a lot of errors and they don't read very well. So if I'm reading and it sounds kind of choppy and bad, a lot of times I'm trying to adjust as I read. But let's try it and hopefully it helps. The braking distance D1 is the distance a vehicle will go from the point when it brakes to when it comes to a complete stop. It depends on the original speed V and on the coefficient of friction, I'll call mu, between the tires and the road surface. The braking distance is one of 2 principal components of the total stopping distance. The other component is the reaction distance, which is the product of the speed and the perception reaction time of the driver. So imagine you're trying to stop, maybe a ball rolls out in front of the road. It takes you some amount of time to process that there's a danger, maybe of a kid running after the ball, or you begin your physical reaction to put your foot on the pedal. And then there's that time that it takes the machine itself to stop once you've slammed the brakes and it's sort of locking those tires up and your car is sliding. So that's what they're talking about there. The kinetic energy E is 1/2 times m times, I think they mean to say v squared there. The work W given by braking is mu times m times g times d1. They'll talk about what those variable values are. Equaling E and W gives the braking distance. D1 equals v squared divided by 2 times mu times g, where g is the gravity of Earth and m is the vehicle's mass. We have v in kilometers per hour. G is 9.81 meters per second squared. And in the following, we suppose that the reaction time is constant and equal to 1 second. That's a very nice simplification for us. The coefficient mu is dimensionless. So the tasks are, the first one is to calculate the total stopping distance in meters given v and mu. And again, the reaction time is 1 second. So this is what our function is going to look like, the sort of signature, if you will. And then what we're going to focus on this first. Eventually we'll get to this second one where we're going to calculate v in kilometers per hour, knowing d in meters and mu, with the supposition that the reaction time is still 1 second. So it's kind of like what we did in the first part, but just instead deriving that speed from d and mu. They give a couple example values, which I don't know if they're that helpful, but if you like, you can consider them. Notes: remember to convert the velocity from kilometers per hour to meters per second, or from meters per second to kilometers per hour when necessary. Don't forget the reaction time, t equals 1 second. Don't truncate or round your results. See and run sample tests, the function assert fuzzy equals or do test. Shell only dist is tested. That won't apply to us. They're going to test both dist and speed. If they didn't, then I would just do distance. But you can see they have distance tests below and braking speed below. So feel free to pause and try this one out. If you get stuck, come on back. We're going to do the distance one first. And I'm going to set up a constant for that gravity. I'll call it, actually, let's do this. I like to keep my public stuff at the top. Private, static, read-only value. We'll make it a double, and we're going to name it gravity. And we'll say 9.81 meters per second squared, right? So we've got gravity, good. And then they essentially gave us the formula for distance, right? It was right here, d1, which is what we have to return. We have to find this distance. But they gave us the equation. This is what we have to implement. The catch is is that, remember, V is given in kilometers per hour, and we need to get that in meters per second, so we're working with the same units. Remember, gravity's in meters per second squared. We got to compare apples to apples there. So for that, I'm going to make a little helper function to convert private static double, let's call it km per hour to meters per second. And I'll take a double representing the kilometers per hour. And we just got to convert that, right? So that'll be handy for us. So to convert from, we want to go from km per hour to meters per second. Let's see, how do you get from, let's go to meters first, right? Convert to meters. And for this, we can say meters per hour would be equal to the kilometers per hour. And then what we can do is say that we know that there are 1,000 meters for every kilometer, right? And so essentially you can see that the kilometers on top here cancels out with the kilometers on bottom there. And as a result, what we have to do is essentially multiply by 1,000, right? Because there are 1,000 meters for every kilometer. You can imagine if you had a value of 1 kilometer per hour and someone asked you how many meters per hour is that, you would just multiply that 1 by 1,000, right? You'd say 1,000 meters per hour. So good. We know how to do that, but then we have a second part here, convert to seconds. And the same kind of thing, right? Where we had meters per hour, but now we need to get seconds. And I'm putting, notice how I'm up here, I put the kilometers on bottom to cancel out with the value on top. Since the hours are on bottom here, I'm going to put that on top. And there are 3,600 seconds in an hour, right? There are 60 seconds in a minute, and if you multiply that by 60 minutes, you get 3,600. And so essentially what you see here is that we divide by 3,600 to convert that value into seconds. And so when you put this all together, you get something like kilometers per hour times 1,000 over 3,600, right? If you multiply by that ratio, then we get down to the meters per second. And so that's the same as, we can reduce that, so it's, to simplify it, if you divide it by 200, it should go down to 5 over 18. And so if we multiply the passed-in ratio by that, we should end up with meters per second. So I can say return km per hour times that ratio times 5.0 over 18.0 f, floating point values. Okay, so that helps us. Let's take that then and sort of right off the bat for distance, let's convert that velocity so our units all match up. So we could say double, I'll call it ms for short. We'll think of that like meters per second. Maybe that's a little too short. Meters per, how about that? And we could simply pass v in there. And then we have our conversion done, right? And so our result now, we can implement that method they gave us. So you could take meters per second times meter per second. I'll use the math power function that we've seen before, meters per second, and raise it to the second power. That's the same as multiplying it by itself, right? So we've got that speed squared. And then it said to divide that by this quantity, 2 times mu, which they gave us right there, mu, and then g, which represented gravity when we set up our constant for that. So maybe it'll help if I expand that, see gravity. So that covers the braking distance of the machine, and then remember they said to also include the reaction, which is 1 second. So that works out very handy here, right? Because we have this value in meters per second, so we can actually add the extra meters right on. We don't even have to multiply it by anything. We don't have to scale it. We can just simply say meters per second. And that should cover us. Maybe I'll do a log so we can see how this is looking. Console, right line, and we'll give it, let's take our input, v equals v, mu equals mu, and result equals result. Result's not part of the input. I'll say output, something like that. It doesn't matter, as long as you can see your values. And then we can return the result. And so, again, you didn't have to set up this variable. I just did it so we could print out some values in case anything's going wrong, and that might give us a little more insight. So at this point, I suppose I'll run a test just to check on the distance method. It'll obviously blow up for these speed ones. Let's just return -1.0 so we don't get an error. I got system library to use this console write line. I'm going to get out of full screen so we can see the test. Let's see if we can at least pass the distance test. Obviously the speed's going to fail, but look, distance looks good, right? Test 1 has all these distance classes down here. See, 144 and 0.3 returned that. You can see it's pretty close. Ours is a little different, right? It's got this 4592 at the end, but it's within, it's very close. So their assert fuzzy equals is good. So yeah, that's good. We got the distance down. That's the first part. That'll allow us to solve the second part. So let's move on to handling the speed. And so let's think about this. What did they give us? We had the speed given the parameters d and mu. That was it, wasn't it? Yeah, d and mu should return a velocity. Because they used v, they're expecting kilometers per hour, so we have some potential conversion again to do there. And it was such that dist v mu returned d, right? The d in this parameter. So you can see how the relationship between the two. Okay. And so I already have dist v mu equals d, right? That's what we did for the distance method. We have that. So we can take that, right, and solve it for the v value. All the other values are known, and so other values, we're not dealing with a bunch of variables, right? We know the values of all of them except for one. So we can solve for a single variable. And then this equation, right, that returns v is exactly what we need for speed, right? That's precisely what we're looking for. And so let's take that last method we made, and it said d, the distance, right, was equal to, I'm going to use the meters per second because that's the units we worked in. It was meters per second squared. I'm going to use this shorthand. Meters per second squared, right, divided by the quantity 2 times mu times gravity. And then we added another meters per second. If you don't recall that, remember, it's precisely this, right? So, and then we can solve this equation. I capitalize all of the variables that are known values at this time, and I left meters per second lowercase because that's what we're looking for. And I was just hoping to highlight the fact that we only have one variable here, and we're going to solve for it. And we'll make a note, then convert from ms to km per h, right? From meters per second to kilometers per hour. That's the units they're expecting for this output here. So now we're at the point of solving for meters per second, right? And to do that, we can use the general form equation. Hopefully you remember this: ax squared plus bx plus c equals 0. If we put our equation in this form, we can use the quadratic equation to solve for these coefficients. Hopefully you remember this from algebra class, but you can search for general form equation if you don't recall that. So that's the strategy I'm going to use here. So I can basically rewrite this, right? I'm going to sort of break this first term here out. I'm going to separate it out into a coefficient that leads the meters per second squared. And meters per second we can think of as x here, right? So let's rewrite it that way. In that case, we would have 1 over the quantity 2 times mu times gravity, right? You can think of it as 1 over that times, I'll just write it right next to it. Maybe that will look more coefficient-like. I'll group it all together so it looks like a fraction. This would probably look better if I wrote it out by hand. I don't have anything handy to do that. So we'll have meters per second squared. So can you kind of see how this is the a term now? Ax squared plus we have our b term, which in this case is just the ms from the equation. Remember this part? That's an x, so we can just say plus meters per second, where it's implied that the b value is 1, right? Coefficient there. And then to get the c term, which is just a constant, we had d on this side, right? So we'd have to subtract it over to this side of the equation, and that'll cancel this out. It'll make it a 0. If we subtract d from d, we're left with 0, and then we subtract from this side of the equation to keep the equivalency. So we have to say minus d equals 0. And then look at this, we have our general form. We have our a term, the b term is 1, and our c term is negative d. So we're going to use something, we're going to use the quadratic equation to get the roots of this general form equation. and I had gone searching to see if C# had anything built in, like the quadratic equation. I didn't see anything from a quick search, but it led me to Stack Overflow, where I saw someone had implemented a form here. So we'll just copy that. If you wanted to see the quadratic formula, maybe this looks familiar, right? Negative b plus or minus the square root of b squared minus 4ac all over 2a, right? When you have the general form of the equation, which we just did. So feel free to review that if you like. Someone had implemented it here. So you know what? I can just grab it, copy it. We'll bring it in and make that a method over here that we can use. Paste it in. Bear with my OCD, please. Okay. And so, yeah, I'm going to add the private. I like to be explicit with that. If you don't type private, it just defaults to private, but I think it looks nicer, and I like being explicit, so that's why I do that. You know what, I'm gonna capitalize that. Quadratic formula, quad form they called it. So, the pre-root you could think of like this part, right? They won't let me highlight. But the b squared minus 4ac would be that. If it's less than 0, we're not going to deal with imaginary numbers. Remember, you can't take the square root of a negative value unless you're dealing with imaginary numbers. So we'll just say return double.nan. nan means not a number. We shouldn't hit this case, but it's there if we need it. OCD again. We're returning here, so there's no point of having an else. This logic will only run if the pre-root's greater than or equal to 0. So that was a lot of extra garbage in my opinion, so I'm removing it. Make it your own, right? And then we had this pre-root var sign positive -1, return the sign times. Hopefully you can kind of see the you can see how this matches up with the quadratic formula. And notice how it has the plus minus. That just means you're doing one version where you add and one version where you subtract. That's where that comes from. So you'll get 2 roots. So yeah, now that we have this quadratic formula, we can go ahead and use it in our speed method. We can calculate 2 roots, right? So to get back to that, let's say double root 1. And for this one, our first root, we can use quad form. And we have to pass in the coefficients, right? A, B, C. And then we have the plus version and the minus version, right? So we'll actually make 2 lines with the root 2 we'll make after this one. So for the first argument, we said it was that 1.0 divided by the quantity 2 times mu times gravity, right? That was our coefficient right here. And I think I got my parentheses lined up. That was our first coefficient. The second coefficient was 1.0. And, oh, you know what? One thing about that, this likely isn't going to come out as an integer, so I'm going to just make mine doubles. There we go. 1.0, and then our third parameter was -d. That was our coefficient, right? Our c value was -d. And then we'll do one where it's positive, where it's adding, right? We had plus or minus. And then we can copy this and say root 2 is all the same stuff, but just false. to get the subtraction. And so at this point we have two roots. Maybe I'll log those. Console write line root 1 equals root 1. Root 2 equals root 2. This is optional. Okay. So we've logged those. Basically, I'm just going to take whatever root comes out positive. If that's the first one, great. If root 1 is greater than 0, I'm going to return it. But remember, we did our calculations in meters per second, right? And they're expecting a v value in kilometers per hour. So we have to convert back. If you look at what we did in kilometers per hour to meters per second, we multiplied by 5/18. To go back the other way, we can do the reciprocal, right? We can say root 1 times 18.0 over 5.0. And you could make another, if you want to do another method that was meters per second to kilometers per hour, you could call that here. You know, if you want to make a method for that, I'll just leave it like this. Okay, so we have to cover the case that root 1 wasn't the positive one. And I'll just say return root 2 times 18.0. Otherwise, return that one. And yeah, I think that covers us. That should convert the value back to v, assuming our quadratic formula works right. Seem to have some good feedback on the Stack Overflow page. So I guess we'll get out of here and try testing that. We had passed the d's. Let's run it with our speed function. Great, lots of green, that's what we like. And so you could expand these if you wanted to see what kind of roots you were getting. See on the second one how they're negative. So yeah, I didn't want to use, I didn't want a negative velocity, right? So yeah, we take the sensible answer, the one that the answer that the root that makes sense for our problem. So that's why I did that. I guess we'll go ahead and run the larger suite. Good, nailed them. Yeah, can expand those and look through those if you like. I'm going to go ahead and remove my print statements before I submit. Maybe I'll just say return that, since I'm not logging it anymore. And then I'll leave the comments. They may be helpful for someone else. If our answer shows up in the feed for someone, maybe that will, so maybe somebody will like that, I don't know. Yeah. Oh, extra white space there, clean that up. Stay tidy, right? Yeah, that looks good. I have to run the attempt again because I modified the code. No expected changes there. And good. I'll go ahead and submit. We'll check this out. Maybe people had a lot better ways of doing this. Static double, okay. Squared, yeah, that was essentially the equation that was provided. They didn't go to the trouble of making constant like we did. That's fine. It's just kind of a throwaway problem. But yeah. Feel free to review those. Yeah, otherwise, hit me up with questions or comments, and then we'll move on to the next challenge. Thanks for watching.